Causal research design. Experimentation is commonly used to infer causal relationships. The concept of causality requires some explanation. The scientific concept of causality is complex. Causality means something quite different to the average person on the street than to a scientist. A statement such as X causes Y will have the following meaning to an ordinary person and to a scientist. The ordinary meaning is that X is the only cause of Y, and X must always lead to Y. The ordinary person thinks that it's possible to prove that X is the cause of Y. On the other hand, the scientific meaning is that X is only one of several possible causes of Y. The occurrence of X makes the occurrence of Y more probable. That means that X is a probabilistic cause of Y. From a scientific point of view, we can never prove that X is the cause of Y. At best, we can infer that X is a cause of Y. The scientific meaning of causality is more appropriate to marketing research than is the everyday meaning. Marketing effects are caused by multiple variables, and the relationship between cause and effect tends to be probabilistic. Moreover, we can never prove causality. We cannot demonstrate it conclusively. We can only infer a cause and effect relationship. In other words, it's possible that the true causal relation, if one exists, will not have been identified. Understanding the conditions for causality helps clarify the concept of causality. Before making causal inferences or assuming causality, three conditions must be satisfied. These conditions are necessary but not sufficient to demonstrate causality. No one of these three conditions, nor all three conditions combined, can demonstrate decisively that a causal relationship exists. Concomitant variation is the extent to which a cause X and an effect Y occur together or vary in the way predicted by the research hypothesis. Evidence pertaining to concomitant variation can be obtained by qualitative or quantitative methods. The second condition is time order of occurrence of the variables. This states that the causing event X must not occur after the effect Y. By definition, an effect cannot be produced by an event that occurs after the effect has taken place. It is possible, however, for each event in a relationship to be both a cause and an effect of the other event. In other words, a variable can be both a cause and an effect in the same causal relationship. To illustrate, customers who shop frequently in a particular supermarket are more likely to have a loyalty card for that supermarket. In addition, customers who have a loyalty card for their supermarket are likely to shop there frequently. The third condition is elimination of other possible causal factors. With experimental designs, it's possible to control some of the other causal factors. It's also possible to balance the effects of some of the uncontrolled variables so that only random variations resulting from those uncontrolled variables will be measured. Here are some of the basic concepts and definitions. Independent variables are variables that are manipulated. That is, the levels of these variables are changed by the researcher. These variables are also known as treatments, and they may include any change in the marketing mix, such as price levels, package designs, or advertising themes. Test units are individuals, organizations, or other entities whose response to the independent variables or treatments is being measured. Test units may include consumers, stores, or geographic areas. Dependent variables are the variables that measure the effects of the independent variables on the test units. These variables may include sales, profits, attitudes, and likability of the product. Extraneous variables are all variables other than the independent variables that affect the responses of the test units. These variables confound the dependent variable measures in a way that weakens or invalidates the results of the experiment. An experiment is formed when the researcher manipulates one or more independent variables and measures their effect on one or more dependent variables, while controlling for the effect of extraneous variables. An experimental design is a set of procedures. Number 1. The test units, and how these units are to be divided into homogeneous subsamples. 2. What independent variables or treatments are to be manipulated. And 3. What dependent variables are to be measured. 4. How the extraneous variables are to be controlled. Extraneous variables represent explanations of experimental results. Unless they're controlled, they may affect the dependent variable and thus confound the results. There are at least 3 ways of controlling extraneous variables. Randomization refers to the random assignment of test units to experimental groups. Treatment conditions are also randomly assigned to experimental groups. As a result of random assignment, extraneous factors can be represented equally in each treatment condition. Matching involves comparing test units on a set of key background variables before assigning them to treatment conditions. Design control involves the use of experiments designed to control specific extraneous variables. There are many different types of experimental designs. One of these is called a before and after with control group design. The test units are randomly assigned to an experimental group and a control group, so that the size of each group is equal. The random assignment assures that there are only random differences between the 2 groups. In this slide, as you read from left to right, time advances. Look at the rows for the experimental group and the control group. The R stands for random assignment. A pre-treatment measure is taken on each group. These are the O.1 and O.3. Then the treatment, which is X, is applied to the experimental group, and a post-treatment measure is taken from both groups. The treatment effect is O.2 minus O.1, all minus O.4 minus O.3. This design controls for most extraneous variables, and selection bias is eliminated by randomization. A factorial design is used to measure the effects of 2 or more independent variables at various levels. Factorial designs allow for measuring interactions between independent variables. A factorial design can be conceptualized as a table. In a 2-factor design, each level of one variable represents a row, and each level of another variable represents a column. Factorial designs involve a cell for every possible combination of the treatment variables. This slide shows a 2x2 factorial design. We're measuring the impact of 2 independent variables, also called factors, on the likability of pizza. So the likability of pizza is the dependent variable. Each factor has 2 levels. The 2 factors are thickness of the crust, 1/4 inch and 3/4 of an inch, and the spiciness of the sauce, 1/4 teaspoon of cayenne pepper and 1/2 teaspoon of cayenne pepper. I'll call these thick and thin crust and mild and hot sauces. The test units are a sample of 1,000 college students. The students are randomly divided into 4 groups of 250 students in each group. Each group of 250 students samples one of the 4 pizza recipes. The dependent variable is likability of the pizza on a scale of 1 to 10, with higher scores indicating more likable pizza. The numbers in this table are the average likability scores. When you look at the scores for mild and hot sauces, they both have an average score of 6, so you might be tempted to infer no difference in likability based on the spiciness of the sauce. The thin crust scored a little higher with an average of 7 than the thick crust that had an average of 5. One feature of factorial designs like this is that you can look for interactions between the levels of crust and the levels of spiciness of the sauce. You evaluate interaction by comparing the averages in the individual cells of the table. Notice that the combination of thin crust and hot sauce had the highest score with an average of 8. The inference is that thin crust and hot sauce caused the students to like the pizza more. That's a look at causal research design. Thanks for watching.